All right, in section 6.5, we will learn more methods in determining whether or not our data or our population comes from a normal distribution. So we have the following pictures to analyze. Let's take a look. So if we have a normal curve, what we're going to learn today is called a, sometimes called a QQ plot or a normal quantile plot. And what it does is it takes your data, so this is an x-axis, this is an x-axis, and then it plots the z-scores of your data. Okay, and if you have a normal curve, a symmetric normal curve, you will get a very straight line. So this will be very straight, these z-scores that you plot. And we want that. So we want a straight line with no patterns. Okay? So today's pretty simple because a lot of what we're going to do today is just look at a normal quantile plot and decide is it straight or not, which is a pretty simple thing to do. It's a little harder to make the plots, but I'll show you tools on the computer to make them so you don't have to do it by hand. Okay, let's see what would happen if we have a pattern. So if you were to have a uniform distribution, so let me write this. This is normal, this is uniform, and you plotted the z-scores for this. You would get something that looks like this. Okay, so you have this pattern in here. So this is a pattern. Now, patterns aren't bad necessarily because it means that there is some connection between your x value and the y value. So there is a connection here, but we want normal data. So if we find a pattern, we're going to say it's not normal. Okay, let's look at one more that we might come across. So if you had a skewed normal curve, so and you'll recall this is skewed to the right, and I could have skewed left too, but if you have some kind of skew going on, it will look like this when you plot the normal quantile plot. It'll have this sharp jump and then it'll taper off. So these two, although they can tell us something, in this course we don't want to see these. We only want to see this one, the straight line pattern. Okay, so that's pretty much the theory. Looking for straight line quantile plots. So let's look at problem 41. If you selected random sample of M&M plain candies and construct a normal quantile plot of their weights, what pattern would you expect in the graphs? So M&Ms, especially if you pick a large sample, 1,000, 2,000 M&Ms, something like that, they will definitely fit a normal curve when you start weighing them. So you would expect approximately a straight line pattern for those weights. And that's true of anything that's manufactured. So any time you manufacture something, if you collect 100 or 1,000, it could be bolts, it could be washers, it could be candies, and you weigh them, measure them in any sort of way, they will all fit a very nice normal curve. Because we can't make things exact every single time. There'll be slight differences in each. Okay, 42. So here they give us a quantile plot. This is, the right represents duration times of eruptions of a certain geyser from the accompanying data set. Examine the normal quantile plot. So they give you this data set of durations. There's a bunch of them here. And we don't really need to see this. All we need to see is the normal quantile plot. And the whole thing today is we're trying to see, does it fit a straight line pattern? And they've made life easy for us. They've given us the straight line that they think it should fit. I think it's pretty reasonable. All of us would come up here and say, is this a straight line pattern, these dots? No, right? So I don't think any student in here would say, yeah, that's a straight line pattern. I would say no. If it's not a straight line, that means the distribution is not normal. So not normal, not normal, is normal, is normal. Those two are gone. The distribution is not normal. The points do not show any systemic pattern. So we don't want a systematic pattern. So you wouldn't want this. So it has to be B. The points are not reasonably close. Wait. Oh, no, I'm wrong. The points are not reasonably close to a straight line. That one's wrong. So it's not B. I made the mistake here. I forgot these words here. Do not show. That's good. You do not want a pattern. So A is right. You do not want a pattern. And we'll see one where it looks very straight, but there's a pattern in it. And then we say, ooh, that's going to make us stop. Okay, so do not show a pattern. That's good. Okay, so that's it for 42. 43. Examine the normal quantile plot and determine whether it depicts sample data from a population with a normal distribution. So if you look at this, the dots are very close to the straight line, right? And we'd all be tempted to say, yes, this is really close to a straight line, so that's normal data. But if you look really close here, there's a pattern here, which is bad. So the dots go up, and then they come down, and they go up again. And this is a very, looks like a, kind of like a sine curve. And so that's going to match what we said before. And I exaggerated when I drew it before. That's going to be close to a uniform distribution. So that is not a normal distribution. So we would say, no, the points do not lie close to a straight line. So they are close to a straight line, so I can't say this one. No, the points exhibit some systematic pattern. That is not a straight line pattern. Okay, 44. The challenge to this one is they give you 1, 2, 3, 4, 5, 6, 10 by 4. They give you 40 numbers. And they want you to generate these two curves. So we'll do a couple problems where we do this by hand, but to do 40 data points by hand would be would take a long time. So let me show you the steps on the computer to do this. Let's see what we're looking at first. Sample data for the arrival delay times in minutes of airline flights is given below. Determine whether they appear to be from a population with a normal distribution. Assume that this requirement is loose in the sense that the population distribution need not be exactly normal, but it must be a distribution that is roughly bell-shaped. Okay, so what we want is to build this quantile plot with Statcrunch. So let's put the steps down for that. So in this problem, there'll be a little table symbol, which you'll click, and that will open up this data table. Then towards the top right, there will be a window within a window. You'll click that, and then you'll say open in Statcrunch. And then you'll choose the graph option. And then there'll be an option called Quantile Plot. So that will give us our quantile plot. You'll click variable 1 to load all this data into the first column. Then you'll check a checkbox that says normal quantiles on the y-axis. Because we want those z-scores on the y-axis like they were for all these other problems. Okay, then you will click, compute. Okay, so this is for, let me mark this as for the quantile plot. Because you actually have to do two things here. You also have to make a histogram out of this data. So to make a histogram out of this, you're going to follow these exact same steps up into the point of graph. So you're going to do all these same 4 steps here to get to the graph, but then after graph, you're going to select histogram. And then for this one, you just have to click variable 1 and then just click compute. So there's less work on this one. Okay, so for this one, they want both pictures, the QQ plot or the quantile plot and the histogram. And for these numbers, here's what it would look like. So the QQ plot would look like this. X, z-scores. And it'll show like a straight line that goes like that. So based on this picture, would you say that it is normal? Let me give you one more picture. So I see some head shaking, that's good. So these dots do not look reasonably close to a straight line to me. And then to confirm it, we look at the histogram, and it looks like this in this problem. So this histogram is also, I mean, if I drew it, the connection, it would look something like this. Definitely not a bell shape, right? So in this one, both the pictures, both the graphs show us that this is not normal distribution. Okay, so then we just go back up and find the right answer. It says, is the requirement of a normal distribution satisfied? We would say no. So these yeses are gone. No, because the histogram of the data is not bell-shaped. That's true. There is more than one outlier. This would be considered an outlier because it's way away from the others. Outlier. and the points in the normal quantile plot do not lie reasonably close to a straight line. So that's all the correct verbiage for what we saw in those two pictures. So A. D is wrong, even though it says no, D is wrong because it says the histogram of the data is bell-shaped, which we confirmed it was not. Okay, so these problems aren't bad if you let the computer do the work for you. Just have it plotted up quick, and you'll be able to see it. Let's go to 45. Use a calculator or computer software to generate a normal quantile plot for the data in the accompanying table, then determine whether the data come from a normally distributed population. So they have space flight durations in hours, and they give you this table. So to do this problem, you use the same steps as before. So same steps as in 44. And you only need the quantile plot, only QQ plot. And if you do that for this problem, your quantile plot will look just like C. And now we can interpret if it's a normal distribution or not. So if we look really closely at it, they're really close to the straight line. I can't see any kind of pattern in there. So we've got very straight line, no pattern. So that is a very good sign of normal distribution. So in this one, the distribution is normal. So our two options are A and D. The distribution is normal. The points show a systematic pattern that is not a straight line pattern. They do show a straight line pattern. So it must be D. The distribution is normal. The points are reasonably close to a straight line and do not show any pattern that is not a straight line pattern. Perfect. Okay, 46. Same kind of deal. This time they're looking at systolic blood pressures of, looks like another 40 people. Around 40 it looks like. And so, same steps for the computer to do this. So same steps for QQ plot. And that's all you need is the QQ plot for this one. And it turns out for this data that they give you, it will look like D. And so now we can interpret. There's just a few dots over here that aren't on the straight line, but other than that, pretty much all the dots are really close to the straight line. Again, I don't see any pattern, so no pattern. I see it's very straight. So I think we'd all argue again that this is a normal distribution. So does it come from a normal distribution? Yes. So these two no's are gone. Yes, because the pattern of the points in the normal quantile plot is reasonably close to a straight line. That sounds good, but let's see if there's a better answer. Yes, but the points in the normal quantile plot do not lie reasonably close to a straight line. They do lie reasonably close to a straight line. So it must be A. Is this pretty simple? Just looking at straight lines, deciding if it's close enough. Okay, Well, just when we think it feels pretty easy, let's go to the hard one. So there is a hard one in this set, and it's right here, 47. So in this one, they want us to do it by hand. A sample of human brain volumes in cubic centimeters is given below. Use the given data values to identify the corresponding z-scores that are used for a normal quantile plot. Then identify the coordinates of each point in the quantile plot. Construct the normal quantile plot, then determine whether the data appears to be from a population with a normal distribution. So you can use the QQ plot to get the right shape, but it will not give you the right numbers here. So these numbers we have to find by hand. But for this part, you would use same steps for QQ plot. And then you can use that to answer this. So you could do half of this problem without doing the hard work. But let's show the hard work to get the z-scores for these different numbers. So the first thing we have to know is how many numbers do we have? 1, 2, 3, 4, 5, 6, 7, 8. So n is 8. Then the second thing is we have to put these orders in number. We have to put these numbers in order from lowest to biggest. So I see 956 first. Then it should be 1026, 1042, 1061, 1070, 1074, another 1074, and then a 1435. So this line is in order. Okay, now we're going to go down to the bottom of the page and we're going to form a table. So we go down here, and luckily there's a pattern here, so you'll see it after we do a couple. You start with writing one over 2n, 3 over 2n, 5 over 2n, 7 over 2n. Does anyone see the pattern yet? What am I doing? Just odd numbers. 9 over 2n, 1, 2, 3, 4, 5, 11, 13, 15. And I stop because n was 8. So if n was 8, you have 8 of these. So 1, 2, 3, 4, 5, 6, 7, 8. If n is 8, though, then this is just 2 times 8, which is 16. So this is really 1/16, 3/16, all the way up to 15 over 16. Okay, and then we're going to find the decimal equivalent of these fractions, and we're going to say that that's the area to the left of our z-score. So 1 over 16 is 0.0625. I'm going to leave off the leading 0 just so I have more space. 3 over 16 is 0.1875. 5 over 16 is 0.3125. 0.4375. 0.5625. Does everyone know what I'm doing here? So I'm just giving you the decimal equivalents of these fractions that we just wrote down. 6875 is the next one. 8125. 0.9375. Okay, now these are the areas that we're going to look up in our z-chart. So I'm going to look for an area of 0.0625. And let's just say I happen to start with the positive z-score table. I'm looking in here for 0.0625. Here's 0.5, 0.90, so they're getting bigger. And my smallest number is 0.5. That's way too big. So let's flip to the negative. Negative z-score. Okay, here we go. 0.003. Here's 0.04. 0.06. 0.0625 is going to be in between 630 and 618. Turns out that 630 is closest. So our z-score will be minus 1.5, 3. So it's minus 1.5, go straight over, and then go straight up for the hundredths place, 3. So this score is minus 1.53. Now I'm going to show you a shortcut. Let's look at the last one, 0.9375. .9375 would be right here. 937, 938, so it's 9370 is closer than 9382, so the z-score is 1.53. 1.53. And what do you notice about these two numbers that we've written down? They're the same. So these problems are symmetric. So whatever number we get here, over here it's the same number except it's positive. So all we really have to do is half of this. Just get these 4, and that'll give us the last 4. So let's do one more for practice. 0.1875. It's going to be negative again because it's still small. 0.1875. Here's 0.1867. That's closest. And that's a z-score of, let's see if I can show it. I can't. It's negative 0.89. So negative 0.89. Negative 0.89, which means this one, second to last, is positive 0.89. Okay, if you look up the rest of these areas on your z-chart, you will get negative 0.49, which makes this one positive 0.49. And you'll get negative 0.16, and this is therefore positive 0.16. Okay, now these z-scores are tied to the x values that we had written down before, the ones that were in order. So these 8 numbers that we put in order match these down here. So our x values were 956, 1026, 1042. The only reason I'm writing these down here is just so you can more easily see that they're tied together, they're matched. 1070. 2 1074s, and then a 1435. Okay. Then it says, list the z-scores for the normal quantile plot. That's just these 8 z-scores we wrote. So you would just type these in up here. Minus 1 point, I'm not going to write them all, but just to show you the pattern so you can see it later. Minus 1.53, negative 0.89. Your last one's 1.53. Your second to last one's positive 0.89. And then the rest go in here. Then they want you to type the ordered pairs. So the ordered pairs are each x value with its z-score. So this first one would be 956, comma, negative 1.53. This one would be the x value of 1026, so the ones in order. 1026, comma, negative 0.89. And then you'd fill these in. Your last answer would be 1435, comma, 1.53, positive 1.53. And your second to last would be 1074, comma, positive 0.89. So that's how you do that part. And then if you wanted to, you could plot these by hand. So these are just ordered pairs. You could plot them on a graph, or you can use those same steps for QQ plot. And if you do it, it turns out that these data points fit picture A the best. And this class is more interested in the interpretation, less interested in this, data crunching, but it doesn't hurt to do a little of that. And so hopefully all of us would say, what about this QQ plot? Is it normal? Good. So everyone's pretty much on board with no. So they're not straight line enough. So we go down to our options. The no's have it. Let's get rid of the last two, which are yeses. No, but the points in the normal quantile plot lie reasonably close to a straight line. No, they don't. Got to be B. No, because the points in the normal quantile plot do not lie reasonably close to a straight line. That's the only one in here I would consider difficult. Okay, let's look at the last three, which are more theory. Okay, let's look at 48. They give us men's heights in this table. So we've got a bunch of men's heights in inches. And I've already argued that things like height and weight and all that sort of thing are always normally distributed. So, but this one throws a little wrinkle in it. It says, if 6 inches is added to each height, are the new heights also normally distributed? So let's say that these heights were, let's assume that they were normally distributed, which is a good assumption. So you have a normal curve for the heights as they are. And let's say the center is at 70 inches. That's the mean. If I add 6 inches to every single data point in this curve, all it's going to do is shift this curve 6 inches to the right. So now it's going to be 76. And every point on here is going to shift over by 6, but they're going to still stay normally distributed. Okay. And so if 6 inches is added to the height, are the new heights also normally distributed? The answer is yes. So adding numbers, as long as you do it to every single data value in the list, will not change the shape of the distribution. Okay, the next one says, if each height is converted from inches to meters, are the heights normally distributed? So it's 70 here, then they change it to meters, and now the center is at, 1.7 meters. Does that change the shape? No. So units also don't change the shape. So it will still be normally distributed. Okay, then it says, are the logarithms of normally distributed heights also normally distributed? So what they did there was they took each x value and they took a logarithm of it. And to help you answer this question, here's what would happen. I think I did this in this problem. I took the logarithm of all those data points, and then I did a QQ plot for it, and here's what the QQ plot looked like. What would you say about the straight line aspect of that QQ plot? It's gone, right? So we lost it. So taking a transformation of these numbers with like a log or something, that will lose your normal distribution. So no, they're no longer normal. Okay, 49. Which of the following is not a procedure for determining whether it is reasonable to assume that sample data are from a normal distribution? Identifying outliers. We did do that once, remember? In that one, we saw that outlier, and that hurt the normal condition. Constructing a graph called the normal quantile plot. Well, that's what we've been doing all morning. Visual inspection of a histogram to see if it's roughly bell-shaped. Yes, we did that in one of the problems. So the only one we didn't do was we did not check for the rare event condition of 5% or less. So we don't need that to check the normal condition. Last one, what have we been talking about all morning? Scatter plot, frequency polygon histogram. We've been talking about normal quantile plot. So a normal quantile plot is a graph of points x and y where each x value is from the original set of data and each y value is the z-score. And that will complete section 6.5.